So, welcome to this talk, the final talk of the series. The title is Hydrogen Detection at High Spatial Resolution and Sensitivity, a Kelvin probe approach. So what I want to do first is to give you an introduction in my research and then a short introduction in Kelvin probe and electrochemistry. Because Kelvin probe, we use it as an electrochemical method, and all what we do based for hydrogen detection is based on electrochemical techniques. So first, an introduction to my research. What we do is hydrogen detection is one topic, one important topic of my research. So that is the talk of today, of course. And then we work with corrosion. So one big topic is also use of Kelvin probe technique, SKP, SKPFM. SKPFM is an AFM-based Kelvin probe technique. For example, for looking for galvanic corrosion coupling. Here, what you see here is a filiform corrosion, and we can see that the topography that is here the potential. We can see the active head live with in situ SKPFM. And then another big topic is coatings. Coatings for corrosion detection. Where we look for fundamental mechanisms of coating delamination, and we are developing also so-called intelligent self-healing coatings. Another big topic is developing novel application for Kelvin probes, and I will show later at the end an example where we can use that to look at, for example, oxygen reduction reaction at buried interfaces, which are not accessible otherwise. And then we have been developed also based on what we do with hydrogen and Kelvin probe, a completely new class of electrodes in the dry, where we can study very fundamental electrochemistry. So first, I will give you an introduction in Kelvin probe and the role of Kelvin probe in electrochemistry. So I will first introduce the so-called absolute electrode potential according to Trasati. So what you see here is a sphere, a metal, and the energy we need to bring up, the lowest energy we need to bring up to take an electron out from this metal to a position outside of the metal. That is called work function. And so that is from the Fermi level, the electron from the Fermi level to a position outside the metal. And if we now have a solvent or electrolyte layer around this metal, we have this case, and we can again define the work to bring out an electron from the metal through the electrolyte layer to a position close outside the electrolyte. And that we can call modified work function. And if we divide that by the unit electric charge, we can call that absolute electrode potential. And as you can see, the absolute electrode potential is composed of three. I will switch on here. The presenter is composed of three parts. So here, that's the chemical potential, so the chemical work you have to bring up divided by the unit charge. Then you go to the double layer here between the metal electrolyte interface. That's this term here. That is where the electrochemistry is located. And then finally, you go outside to the surface of the electrolyte. That is the so-called surface potential or dipole potential of the electrolyte. Okay, so that's the so-called absolute electrode potential. Now, if you look at the third picture here, you see that it looks more like an electrode, right? Immersed in electrolyte. And now you see what we just considered here is this pathway, right? But you can see equivalent from the energetics is also to go outside the metal. That's the work function of this metal here. And then, because metal and electrolyte are charged in respect to each other, there is an electric field outside. So if you go from B to C to the same position as we have before, then we have to go through an electric field. That's a so-called volta potential difference between B and C. Okay, and that is so that means this term here is equivalent to this term, the work function of the metal, and the volta potential difference between point B and C. And if you go a step further and want to find a way to measure this absolute electrode potential, and we put another electrode in contact with our electrode, and it's positioned above the surface of the electrolyte. And now, okay, this term we have already learned, that's the work function, and then from here to here, Yeah. And is equivalent, of course, also to this term. If we go here from the metal, so the wire, there's no energy needed for that. And then the work function of this second electrode, which is called Kp for Kelvin probe, yeah, and plus the Volta potential difference between here and here. Okay, all these terms are equivalent, right? So if we can measure with help of this Kelvin probe the Volta potential difference here, and we have the calibration of the work function for the Kelvin probe, we know exactly the absolute electrode potential of this immersed electrode. Okay, so in a way, this Kelvin probe is a natural method for measuring absolute electrode potentials. How does it work? So a Kelvin probe sample and Kelvin probe form a plate condenser, right? And since I have different work functions, different Fermi levels, yeah, if I make an electric connection between them, yeah, the Fermi levels will align. You can see here. That means the two surfaces of the plates here charge up in respect to each other. This here, from this here, you have electron flow to this side here. So that gets negative and that gets positive. Yeah. So if I now vibrate the plate, the Kelvin probe over the sample surface, then this bias stays constant. And since the capacitance changes, I will have electric flow. Yeah. And if I now apply an external bias until this flow is zero, then it means this external bias compensates this Volta potential difference. We have this case again. Then we null the current. Okay. So by nulling the current, we can measure the Volta potential difference. That's how a Kelvin probe works. Yeah. So the first application has been mainly in UHV, where people were interested in this dipole moment here, dipole potential here. So if molecules adsorb, this will change. You can study that very, very nicely with Kelvin probe techniques. Yeah. What I've just introduced to you is when we have a layer of electrolyte on top. Yeah. Then the additional term I mentioned already is here this potential drop at the metal electrolyte interface. And that is where the electrochemistry will take place. Now, the chemical potential will stay constant in the course of an experiment. The surface potential of the electrolyte too, right? So if something changes, it will be here, this potential drop, the electrochemistry. Yeah. So this way we can measure very nicely, as I explained, the absolute electrode potential. And even if we have a polymer on top, and that's what I mentioned, we are also interested in coatings, organic coatings, and so on. We can likewise measure through the organic coating with the Kelvin probe, measure again the electrode potential at the interface. Yeah, the only additional term in the case of a polymer is then here at this interface, which is called donut potential, but this is usually very small. And upon correct calibration, we can directly measure through the polymer and measure the electrochemistry at the buried interface. So it's a very, very powerful technique. So calibration, you can do the following way. For example, here's a droplet of electrolyte on a gold surface. Here's a Kelvin probe tip. And we can, with help of reference and counter electrode, we can apply here different potentials. And then we can measure and we can see, as you see here, that we get a one-by-one dependence on measured potential and applied potential. That way we can calibrate. And since this is a one-to-one correlation, we just need to know the offset between the two curves. And that can be done standard. That's the way how we do that. You have a copper sulfate electrolyte beaker here. That's a copper beaker inside a saturated copper sulfate solution. We can position this needle here, this Kelvin probe needle over that, and then make a point measurement for calibrating the curve in this offset here. And this way we have the calibration between Kelvin probe signal and electrode potentials versus standard hydrogen electrode, for example, if we recalculate that. So it's really a powerful technique, and it makes no difference between whether the electrode is covered by a layer of electrolyte or the dry surface. Yeah, and that I will explain you in the following. So to get to know the background, in fact. So if you look at this diagram here, you can see the position of the conduction band edge and the valence band edge, so to speak, the band gaps of different oxides. Yeah, and if you look especially in this range here, N-type semiconductor oxides, most of the technical metals we use, the oxides on their surface, the passive layers, are N-type semiconductors, right? So if you freshly polish a metal, then the oxide is highly defective. And for N-side semiconductor, that means you have a very high Fermi level. The Fermi level is just beneath the conduction band edge, right? So for iron, for example, somewhere here. Yeah, that's iron here. So we would expect a freshly covered polished surface. For iron, we would expect a Fermi level position where we would expect a potential, that's here versus hydrogen, around 0 millivolt. And that's what we usually roughly measure if we take a Kelvin probe and position it over the surface of a freshly polished iron. For zinc, we would measure more negative potential. You can see why, because that is here located higher, roughly minus 400 or something like that. Yeah. What's also interesting is for most of these N-type semiconductors, the mid position of the band gap is about in the same position. Yeah. That means if the band gap increases by 2 eV, the conduction band edge shifts up by 1 eV. Likewise, then the Fermi level for the freshly polished surface, right? So what is not 100% correct is we exactly measure this position, because in reality, we don't have a flat band condition on the surface of the oxide, but we have, because there's oxygen, and oxygen wants to take electrons from the Fermi Fermi level, that causes a positive charge at the surface and makes an upwards band bending. Yeah, and here the oxygen is negatively charged, which is adsorbed on the surface. And at some point, this band bending is too high, so there's a barrier for further electron transfer to oxygen. And since it's a passive surface, a dry surface, there's no anodic reaction, no corrosion possible, right? So it charges up until there's no further electron transfer possible, and then it stops. That's the final position. And we found out that's roughly 50 to 100 millivolts. Yeah. So if we measure on different metals the potential with the Kelvin probe and compare that to flat band potential measured electrochemistry, you will find here, shown here for iron and zinc, that the levels for the flat band potentials, the potentials, are a little bit lower than what we see here for the potential measured with Kelvin probe in air. Yeah, because of the band bending upwards. Yeah, roughly, as you can see here, 50 to 100 millivolts. Okay, and what you also can see, if you compare that with the band gap, if the band gap changes by 2 eV, we see here a change of about 1 volt, as I have just explained. So what this shows to you that the Kelvin probe can measure electrochemical potentials, because that are potentials defined by the semiconducting structure of the oxide, but also by oxide reduction, the charging up. Yeah. So what we see here, even on dry surfaces, the potentials measured with the Kelvin probe, if you calibrate versus a reference electrode, are giving us very interesting information about the electrode potential of these materials. Yeah? And that we can use, for example, to look for galvanic elements, because we can use it even with AFM. Even AFM, you can use a Kelvin probe mode. And that way, then you can very nicely study galvanic elements and so on. Yeah. And the best thing is if you do it in situ in your humid atmosphere where corrosion can occur, then you can see live how such corrosion processes occur. But that's not the topic of today. The topic of today is what I call, first I will introduce a hydrogen electrode in the dry, as I call it. That is what we need for the hydrogen detection that I want to show you today. Okay. So the standard technique for measuring hydrogen permeation through materials, so for example, here could be steel or palladium or something, you put the material of interest between two electrochemical half cells. And on one side, you apply a low potential so that hydrogen is loaded into this metal membrane. And on the other side, you apply a high enough potential so that the hydrogen permeating through the membrane is oxidized. Yeah. And if I look at that, usually what you do if you have steel, you coat the entry side and the exit side with palladium to have a high catalytic property. So you have high kinetics for the hydrogen charging and then also for the 100% hydrogen oxidation, in fact. Yeah, and you avoid also that you oxidize the metal if you have a protective palladium layer on the outer side. But what you have is, if you start charging, you start formation of a concentration gradient through the metal, and after a while, you keep that here constant, the activity on the entry side, and here you oxidize all hydrogen. That means after a while you have a linear gradient through the material. Yeah. When you have that, you end up with a final constant permeation current density. Yeah. At the first moment, you don't see anything because it takes a while for the hydrogen to reach the outer side, right? That gives you then an idea about how much hydrogen is trapped in the material. Okay. So that's a standard technique to learn, for example, permeation of hydrogen through materials. Yeah. We had a project where we wanted to study kinetics of the hydrogen uploading here on the entry side. And if you want to study that with a high resolution, time resolution also, it's very important that the membrane is then very thin. So you don't lose too much time for the permeations through the bulk of the material, right? So we calculated for the purpose we want to study, in this case it was electrogalvanizing processes. We needed something like 20 micron or so. If you do that, then single grains can fall out. If you thin out the material so much, full grains can fall out. And then you have, of course, a gap here in the membrane, and you might have a shortcut of the two electrochemical cells, right? So that doesn't work. So what we said is, or what we thought is, if we skip one electrochemical cell, do the charging with one electrochemical cell on the entry side, and on the exit side, we use the electrode in the dry concept, yeah, with a Kelvin probe. Then the surface tension would keep the electrolyte in here, and we can measure point per point, even with high resolution, lateral resolution, because now it's dry. There's no shortcut between here and here. We can analyze different grains, grain boundaries, and so on. That's what's the idea. And what the idea was, what we would measure, for example, if we have a steel, iron covered by iron oxide, if hydrogen comes through the material to the surface and reacts with the oxide, then of course the hydrogen is able to reduce Fe3 plus states, for example, to Fe2 plus states. Yeah, and this way we could measure then the hydrogen permeation through the material. Yeah, as I just explained, the semiconducting structure is changed by this. That works also. And that's also the concept of many applications of Kelvin probe techniques for hydrogen detection and hydrogen permeation, diffusion detection by many groups. But we found out it's very difficult to quantify because oxides are full of defects, and an oxide is not the same as another oxide. So it's very difficult up to impossible to use this approach for a quantified measurement of hydrogen permeation or fusion from a material. So we went a step further and thought about palladium. Palladium is very catalytic for the hydrogen electrode, and we thought, okay, if hydrogen goes through the palladium, on the dry side, we might form a hydrogen electrode. So that we tried out. So what you see here is, here's a palladium membrane, here's an electrochemical cell, and here's a volume where we have a Kelvin probe in dry nitrogen atmosphere. It's important that you have no oxygen because oxygen would react with hydrogen, of course. Yeah. And then we applied different potentials at the entry site in an ideally polarizable range for the palladium electrode. And as you can see, when we go step by step from high potentials where the activity of hydrogen is very low towards a low potentials where we have a high hydrogen activity, you can see there is a 1-by-1 relation between the potential applied here and the potential measured on the dry surface of the palladium on the other side. Yeah, up to a certain point where we don't have any response anymore. And if you look in the Pourbaix diagram for palladium and hydrogen, you find that is exactly there where you form palladium hydride at this point here. So here you have, at this point, you have an equilibrium between palladium with the dissolved hydrogen and the first palladium hydrides forming. And that pins the chemical potential at this point, and that is why we don't have any response anymore. That will change only once we have transformed the whole palladium and the palladium hydride. Okay, and that also works if we have a sandwich sample of a palladium membrane, iron evaporated on that, and a thin palladium layer here on the outer side again. Yeah, even if we have that here for the so-called sandwich sample here, you can see this correlation exists. And that means this equilibrium of the hydrogen is establishing throughout the sandwich sample. And on the surface, again, we see the hydrogen electrode. Okay, now, if we know how activity of hydrogen, so potential here, is reflected in the amount of hydrogen inside this palladium film that we have evaporated here, then we can use the potential as an information for the hydrogen which has entered this palladium layer, this palladium film. It's about 100 nanometer in this case. So we did that with an electrochemical technique, and we found there's a difference between whether you have a thin palladium membrane or a thin evaporated 100 nanometer palladium layer. The dependence between hydrogen concentration and potential is, you would expect, according to the Nernst equation, it should be 60 millivolts per decade, but that's for the activity, in fact. And since the palladium layer, the thin 100 nanometer layer, has a lot of grain boundaries, and the interface between the iron and the palladium plays a big role, activity is not the same as concentration, and that leads to a different slope. So for the thin palladium layer, we have 130 millivolt per decade. But with this quantification now, we can, with calibration between concentration and potential, we can make use now for quantified measurement of hydrogen in materials. So for hydrogen detection and also for permeation measurements in situ with high resolution and high sensitivity. So permeation measurements are the same as I've just explained to you. They're the same thing now. The palladium layer here is now the detection layer. So when hydrogen diffuses through steel, for example, it comes now to the interface with the palladium. And the palladium, the chemical potential is much lower for hydrogen than in the steel. That means it takes up immediately the hydrogen reaching the surface. And that's the same as if you would oxidize the hydrogen, like in the Devanathan cell I have introduced before, right? And we get then increase of hydrogen concentration inside the palladium that looks like this, which is the same thing as the integral of the permeation current over time. Yeah. From that, we can get time lag. So that is again then the trap sites. Here, when the slope gets constant, that's when we have reached the constant permeation current density. Yeah. Likewise, we can use this technique and take a steel sample which contains some hydrogen, and we evaporate a palladium film on top. And now the hydrogen enters the palladium layer. Yeah, so we can measure hydrogen diffusion from the steel, for example, or the aluminum alloy. Yeah, and that it means the chemical potential in the palladium goes slowly upwards, or the concentration. Yeah, and this way we can measure either permeation through steel or aluminum, or we can measure local hydrogen activity, because the release from the steel, for example, to the palladium tells us about the local activity of hydrogen. Not just the concentration, but the activity. That's what was doing the diffusion process, or the release into the palladium, right? So that is shown here. Let's say we have a steel sample. It's locally charged with hydrogen. Here it's a spot. And then we evaporate a thin layer of palladium, for example, 100 nanometer. And now we scan with a Kelvin probe across that surface. And what will happen then, that from trap site and also from the lattice, hydrogen will enter the palladium layer, right? And it takes some time, of course, it will change with time. Yeah, we can follow it at different times. Here's a snapshot. You can see here where the charging was. We see a low potential. Where it was not loaded with hydrogen, you don't see a decrease. Yeah? And since we have the calibration, we can look at each time interval where we do measurements. How did the potential change? And from that, we can calculate release rates locally from the steel into the palladium. That is also shown here. Here we have a palladium film. Here's a steel matrix. Here different trapped sites. Okay. And here you can see, for example, how the chemical potential looks like. And the palladium is much lower here. In the steel, it's here, the hydrogen starts to be depleted because it goes into the palladium. Yeah, so with time, we will see this. And after some time, the release is mainly determined by the release from the trapped sites. Then we get a more or less constant gradient, which changes only very slowly. Yeah, and then we get a more or less constant change of potential with logarithm of time. The reason is the concentration in the steel changes with a constant rate, the release rate from the trapped sites, as I mentioned, roughly constant rate. times time. So if I do the logarithm of that, because according to the Nernst equation I just explained, just that the slope is different, 130 millivolt per decade, we expect a dependence on logarithm of c. Yeah, and as you can see, that is this gives us something proportion to logarithm of the time, in fact, and that's what we see here. We get something like this: potential changes linearly with a logarithm of time. Yeah, and at the position of this line that we get here tells us the exact diffusion current density. You can see it's in this case 240 picoamps per square centimeter. This is the most sensitive technique to measure hydrogen diffusion from materials, especially if you think that we don't measure with a square centimeter tip. It's just a few hundred or 100 micrometer diameter. So the resolution, the sensitivity is even much, much higher than you get here. It's in the femtoamp range or something like that. Unbelievable sensitive technique, right? And we can use it also with AFM and get a very high resolution. Shown here, it's a dual phase deal. It contains austenite and ferrite phases. That's here the topography. And here you can see the potential maps taken with a Kelvin probe mode of the AFM. And you can see with time how on the austenite phases the potential goes down because there is more hydrogen in the austenite phase. The ferrite phase was mainly even depleted before we could start the experiment. Yeah, but what you also see is that there are some spots where you have especially high release rates, and there's some trap site beneath what we can't see, in fact, even in the topography, where you have a quick effusion of hydrogen from. Yeah, so danger sites where you have a high hydrogen supply from. Yeah, this way we can find out, okay, where is hydrogen coming from in a certain material in very high resolution and very high sensitivity. So the principle is explained here. We have more hydrogen in the austenite, and for that reason, we see there more hydrogen coming into the palladium layer. We could do also another experiment with the same sample. Yeah, we charge it from the backside and look how the hydrogen goes through. Now the ferrite is much faster because it takes a long while to saturate the austenite. Yeah, and that you can see here. So the ferrite, you see the decrease in potential much faster than on the austenite phase. For that, of course, you have to thin out the material significantly. Otherwise, you get an average between austenite and ferrite phases where the hydrogen has to diffuse through. Yeah. Another application of that is shown here. We have here an iron alloy with containing 5% nickel, and we want to study hydrogen in this material. I will not go into detail here, but we do TDA, for example, and we get different peaks and want to understand where does the hydrogen come from. And we knew from the characterizations that this material, for example, contains some impurities, some manganese oxide impurities. And one question was, does some of the hydrogen we see in the TDA comes from these oxides? And so what we did is we did SKPFM measurements on different materials. They have different stages: annealed, cold rolled, and recrystallized. Yeah, where we did also get different TDA measurements. And we found that for the cold rolled, for example, and the recrystallized, we can see this is topography here, and this is here potential maps. And we can see with time that from the oxides for the cold rolled and the recrystallized sample, from the oxides, hydrogen is released into the palladium layer. Yeah, so you wonder, okay, we see now that for cold rolled and recrystallized, we can see that hydrogen comes from the oxides. Is it a big amount or not? So with SKPFM, AFM-based techniques, the calibration of the potentials is not so easy. So what we get here is more or less a qualitative image. Yeah, if you want to quantify, you need an idea what does it mean, what we see at potential contrast. So for that reason, we did also an SKP measurement. And where you can see here for annealed, cold rolled, and recrystallized, how these release curves look like, the effusion curves look like that I just explained. And you can see for the annealed and the recrystallized, the effusion of hydrogen to the palladium is by 2 orders of magnitudes lower than for the cold rolled. Yeah, and from that we could conclude, we could calculate that in this release of hydrogen here at these oxide particles plays no role in the TDA peaks. Yeah. But what I want to also show you, that was a high resolution part. It's so powerful, this technique, for also quantified measurements. You can do standard permeation experiments with Kelvin probe like you've done with Van Artan cell. But the interesting thing is, I explained already, you have to also on the exit side to apply palladium layer to protect the steel or the aluminum alloy from oxidation. Otherwise, you get faulty measurements, right? And this deposition of this palladium layer has to be perfect. It's not so easy. In our case now, we don't polarize. We just measure the change of potential in the palladium layer. It doesn't have to be perfect. We just evaporate 100 nanometer palladium. Yeah, so we can do this also on a zinc coating or something like that, which is very difficult to do with Van Artan cell, to deposit their very good qualitative micrometer thick palladium layer or something like that. So we can apply this technique on any surface very easily, right? So we do, for example, I will go show you example for the same alloy I've just shown before. On the permeation measurements, I have to say, if you use Kelvin probe, it looks a bit different. Usually, if you have a permeation cell, the Van Artan cell, you will have the integrated hydrogen amount going through the sample will continue linearly where you have a constant permeation current density. Since at some point our palladium layer will reach the level where you have so much hydrogen inside the palladium layer, where you get this equilibrium between hydride and hydrogens dissolved in palladium, where you get then no potential response anymore, right? So that you have to understand, you have only a certain time where you can measure that. But then you can use that technique, apply it, and for example, here you see permeation measurements done, or results of permeation measurements. It's in the blue colors here with a Kelvin probe, yeah, done on these different materials, cold rolled, recrystallized, and annealed. And here it's compared with an analysis done by TDA. You can see how well this fits. And you can see also the power of this technique. In the annealed and recrystallized sample, the hydrogen was already out of the material before we could start TDA. But because, of course, the permeation measurements, the Kelvin probe is an in situ technique, we can calculate from the time lag very nicely how much hydrogen is in the lattice. Yeah, so you can do this fully quantitative. And what I've shown you here is that we have developed a technique which is highly sensitive and also highly laterally resolved. Yeah. And that is one thing, what we do with this hydrogen electrode in the dry, use it for hydrogen detection in materials. Yeah. And the other approach, I mentioned it shortly at the beginning, is that we can use that also to study, for example, oxide reduction on dry surfaces or buried interfaces. And the idea for that is very simple. That is here the oxide reduction curve in an interface or on a surface. Yeah. And now we have a sample. And from the other side, from the back side, we apply different hydrogen uptake densities. Yeah, these are different hydrogen loading curves that you have here. And if you measure now on the other side, the equilibrium potential of oxide reduction and hydrogen oxidation, yeah, then if all the hydrogen going through the material is oxidized, then it means, and if you know how much goes through the material from the amount which we charge on the backside, then we can also correlate the potentials that we measure here with the current density of hydrogen uptake. And that is the same as the oxide reduction rate at this very potential. That way we can measure even hydrogen oxygen reduction at buried interfaces. Here's an example where you can see oxide reduction measured at a coating, organic coating, palladium interface. Yeah, and you can see we did different polarization measurements. First experiment, second experiment, third experiment. You can see how the curve changes because you get an interfacial degradation. It has to do with the cathodic lamination of organic coatings. This was not accessible before and is now possible to measure with this technique. And we can apply this also on dry surfaces, for example, for fuel cell applications and so on. Yeah, thank you for your attention, and acknowledgements are also listed here. And I'm open for questions.